My driving question for this project was, how is speed maintained when in rotational motion? I chose to apply this concept to the sport of figure skating, more specifically the field of freestyle, which relies heavily on jumps, spins, and turns, and how figure skaters can manipulate their bodies to execute these rotations quickly, smoothly, and as many times in a row as they can. The three main concepts that we are going to be covering in this video are what angular momentum is, how it can be conserved, and how this concept applies to figure skating. So, as a pretty baseline definition, angular momentum is dependent on mass, velocity, and radius. So, this is super similar to linear momentum, which is a quantity of motion based off of mass and velocity. So this is the same thing, just adding in that element of spinning and rotation. And then as a quick refresher, mass is going to be dependent on something's weight, velocity is dependent on something's speed, and then radius is going to be very similar to your distance. So this is going to be kind of like the distance from the axis of rotation. So think of that kind of as like the center of the rotation, and then anything that's kind of hanging off of it or making that axis wider, that's going to be considered your radius. So kind of like in math, same concept, the line from the middle of your circle to the outside, that's going to be your radius. It's going to be the same thing, so anything sticking out of the axis of rotation. So just like linear momentum, angular momentum relies on speed, mass, and rotation, or the size of the circle instead of distance, because it will remain in motion unless enacted upon by another force. So it's just going to keep spinning unless something else is going to stop it or hinder that motion. With this in mind, how can it be conserved? So because no external force is going to be acting upon this momentum, the initial and final angular momentum will equal each other. So your initial mass, velocity, and radius will be equivalent to your final mass, velocity, and radius. So, like I said, these are super similar concepts, lean on each other pretty heavily. And then we're going to apply this concept to skating. So the two main aspects we're going to be focusing on are spinning and jumping. And obviously there are a bunch of different types of spins and jumps, but we're just going to look at a couple today. And then just as a quick refresher, angular momentum does rely on weight distribution and the distance of weight from its axis. So we're going to touch on this a little bit later, but this is just a quick refresher. And then for a bit of history, I mean, like, you can read this, but figure skating became an Olympic sport in 1908. So as you can see, I am not the best freestyle skater, but luckily my friends Vance and Leanne are here to help us out. Let's see what they have to say. So the axel jump is probably the most famous figure skating jump. It was invented in 1882 by figure skater Axel Paulsen, and it's considered the hardest jump in figure skating because it starts from a forward takeoff. So here is my friend Leanne doing that for all of you. As Leanne pulls her arms up and into that axle, she's able to get that extra half rotation she needs, which is why the axle is considered the hardest jump of figure skating. The sit spin was popularized by skater Jackson Haynes in the 20th century, and this is honestly just a really good example of how positioning of weight and distribution can really affect the speed of a spin, because after the skater gets up from that position and pulls off that weight in and they stand up, they are spinning much faster than they were laying down. A twizzle is a type of traveling spin that a lot of skaters use in pair skating, ice dance, and synchro. So my friend Vance is going to do a little jump and then stretch her arms up to maintain that speed, but also have some control by pulling out her free leg and slowing it down to get all of those rotations in and keep that spin going down the ice. If she had her leg in, she'd be able to go much faster, but she would not have as much control of those turns.